Okay, we are back in Sudoku. A little bit different setup. Normally I prefer to do Sudokus with my notations in booklet form because that's all I've ever known to do. I have done online programs and other stuff, but I don't find it very intuitive. Or I guess I don't know if it's more difficult because I can't put my own personal notations. However, I will attempt to apply the X-1 method or formula or whatever you want to call it in conjunction with any other techniques that you may use or I use under anyone's particular names, such as I call them ghost spots or repositories, ghost projections, double ghost projections, all kinds of other names that I have myself because I've developed this, 20, 30 years ago. So it's not it's a self-created concept, not based on anything. I don't know any of the other methods that are supposedly very similar, which I imagine they would be because Sudoku is a game of logic. Interestingly, this particular puzzle that I was challenged or dared to utilize my X-1 formula, I can actually start out with the first answer being a double X-1. And I'm going to show you that on how it'll prove. Now I'm going to apply the first proof I shall do for this first digit using the X-1. I'm going to use the center square, and I put the unknowns. There's three unknowns in there. That would be 4, 5, 6, and applying it to X-1, three unknowns. 3 minus 1 is 2. So 2 of those 4, 5, 6 that cross any square, then the answer is the one that does not cross it. And as you can see, 4 and 6 cross the center one, so that would become 5 under the X-1. Now, alternatively, I can apply X-1 to this center row, and quickly in my head, it's going to be the same number of 3. 3 minus 1 is 2. 2 have to cross it. And the numbers that I'm going to quickly put in my head are a little different than the center square, obviously. And that would be 2, 5, 9. And as you can see, 2 and 9 cross the center square, so the answer has to be 5, which I proved with the other X-1. So we shall put in a 5. Now, like I said, I'm going to go through this puzzle. I'm not sure how it is. It does appear to be a very difficult one, and I think there's a very unique, I call it a quantum X-1 application, and that's coming up later in this tutorial. Now, I got the 5. Now I'm just going to start going through standard projections. I'll bring this standard projection here, not a ghost. 7 down, 7 across, that leaves 1 square for 7. Incidentally, I am going to do this puzzle without notations because normally I do notations on the exterior of my with my booklet, and it's just too cumbersome. So it may take me longer to solve this puzzle. When I do them by myself, I usually solve them 2 to 3 times faster than what you're going to see here because I'm talking. I'm not using my notations. It's a weird environment when you're doing this on the spot. And like I say, I prefer to do, from what I see, is more hard level ones or less. And to each their own. This formula will work with any level. And I'm about to show that. So let's carry on. I see another projection. 3, then this for this square. 3 across, 3 up. That leaves 3 in that location. I'm going to project, standard projection, 3 down, 3 down. 3 becomes deposited. Let's carry on. I'm just scanning. And let's see what. And now what I do is I just quickly in my head. I'm not going to talk through all this because I do it so often. I glance at each square, column, or row, and I quickly run the x-1 formula through that. And I'll do an example. The first one here, so I put 6, 7, 9, and quickly I see 2 7s cross, so that becomes 7 there. Then I can do it with 6, 9 are the two remainders, and that would be 2 minus 1 is 1, and one of the ones of the 6 and 9, which is a 9 crosses, 6 doesn't, 6 becomes the answer. And then the same thing, I can apply it here. 1 unknown, 1 minus 1 is 0. I don't need anything to cross it because the one that doesn't cross it is the answer. And then every time I get an answer, now it allows the formula to work even better because it's dynamically driven, because the variable of unknowns changes with every answer you get. So even if you get a standard projection answer, then you can apply the x-1 formula anywhere that you go so it becomes exciting and is different every time you apply it. So, and I'm just routinely just checking things out. Okay, here's another one right here. You can see 3 unknowns here. That would be quickly in my head 2, 5, 9. That's 3 minus 1 is 2. And I got 5, 9 cross the center one. So that would become the one that does not cross it is the answer. 2. Now I'm just going to carry on quickly. And I can see 5 and 9 are actually in these outside positions. And I'm still doing some puzzle scanning. And this is kind of this is where you got to slow down, because sometimes if you start getting answers, you come to the assumption that you've solved it, and you might move too fast, and that's usually when you make a mistake. So 3, 5. Oh, standard projection, 1 across, 1 down. That's the thing. Sometimes I get going in my formula and I forget to use the standard projections or ghost projections, which will produce answers just the same as the x-1 formula. So it's very good to do them and interchange them, but also stop, look back at the puzzle, and take a broader perspective to the basics of Sudoku. And then I do a projection after getting that one. Project down, 1 down, 1 down. 1 becomes the answer on standard projections. And then quickly we got 2, 4, 8 in my head. Oh, I see a 4 projection, so that puts 4 there. Didn't have to apply the x-1, but almost reposited the numbers into my head. Then we got 2 and 8 here, and 1 left up here, which would be 7. Oh, and 1 left in this row, didn't even really look at it. That would become 8. Then 8 across, 8 across, 8 down, 8 down, that becomes 8. And like I said, these are standard projections, but when you're dealing with, I prefer the hard or medium to hard puzzles, apparently. But the very difficult ones, I understand and I can do them. I may have to use a plethora of my self-designed techniques, which are apparently they have other terms that I'm not really familiar with, because I developed this 25 years ago, probably before those terms were even created, which are the same basically the same type of technique apparently, but I haven't taken the time to learn them, so I'm just going to continue on with my own function. Now I'm going to just standard projection, 7 down, 7 down, 7 across. That leaves a 7 here. Then we got a 4, 6, 9. That produces nothing. We got a 2 and oh, we got a 3 over here. This would or a 3 for my x minus 1, which would be 2, 6, 9. And that produces nothing. Okay, here's a good example. This square down here, throw in my x minus 1. That's going to be a 1, 2, 4. That's 3 minus 1 is 2. They have to cross it. 1 and 4 cross that, so that answer becomes 2 based on the x minus 1 formula. Then that would be 1 and 4. And so vertical projection, horizontal projection produces a ghost. That ghost projection eliminates the 4 and puts it over here. Then that becomes 6. Double standard projection produces 6. And 9 comes in as a result. Standard projection. The remainder is 2. Do another, I can do projections of 2s to get a 2 here, or I can apply x minus 1 to the unknown, the last unknown, which turns out to be 2 anyways. Look back from the puzzle, I do see another when there's 1 left, so that will be 9. And down here, because I know that's 4, 1, so there's only 1 left up here. So that becomes 2 based on, I mean, I could do, sometimes I'll do the x minus 1, sometimes it'll apply, sometimes just standard or ghost projections will result in the same answer. Here's standard projection, 9 across, 9 down. 9 does become there. And this is, I think we're almost getting to the point where we start getting have a stalemate coming up. Oh yeah, over here, standard projection, that produces a 1, then a 4, then we got standard projection, 2 across, that produces 2 and 8. And we got 4, 3. Still looking for more. 2, 3, 4, 5, 7, 8. Oh, standard projection. 2 down, 2 down, 2 across. That puts a 2 there. Then the 3s project down. 3. And then that becomes 4. And I think this is where it pretty much slows down. What do we got? 1, 6, 9. Can't really get much. I'm just going to apply the x minus 1, but I'm going to show this is where you come into it's almost like a future x minus 1 quantum effect. And I'm going to explain that in a second. And I've had this happen several times. This just happens to be one of those times. And I'm sure there is a probability that this theory of the x minus 1 formula may be incorrect, but from whenever I've come across it, if I make the selection I make to induce a x minus 1 result in the future of selections, that can produce the answer. And I will go through and assume that I got it right. I don't even know because I haven't finished the puzzle. I just know that this move is coming up because I did get up to this point earlier and I had to apply it, and I don't even know if I can finish it, but I'm going to explain this point and go from there. Now, if you see standard projections, you got 4 up, and 4 across. So that means there has to be a 4 here or here. So what I'm to induce a x minus 1, I'm going to try, I'm just going to, and this is where I honestly did it this way. I picked the left side as the test. And what happens is if a 4 is there, this square here, using the x minus 1 formula principle, would result in throwing it into my head 4, 5, and 6. But if a 4 is there, that actually crosses 2 of them will, because it's 3 unknowns. 3 minus 1 is 2. And that 4 and that 6 cross, and that induces the x minus 1 formula response, which would turn that into a 5. And then subsequently, so I'm going to put in the 4 now. Just assume that this quantum technique and application and of inducing the x minus 1 to a future event of possibility results in whether or not that answer is correct in that 5, which I'm going to suspect it is. I don't know, because maybe it's wrong. I'll find out eventually, but that is what I'm going with, and I'm going to carry on. So we have, what do we have here? 4 would become down here, then 6 there, and I think now it's pretty much just going to be standard projections, I believe. We shall see. And then we have a standard 8 across, 8 across, 8 up. And this is where I usually make most of my mistakes, because I think I've got the puzzle solved, and I just carry on really fast and end up making mistakes. So projection 8 down, 8 across, 8 becomes there. And I still will apply the x minus 1 formula to fill these in. Let's do it. Let's apply it to this vertical one. That would be 176. And there's 3 unknowns, so you got to find 2 that cross. 1 and 6 cross, so that becomes 7 based on the x minus 1 formula. Then standard 7 vertical projection, 7 horizontal. That produces a 7 answer, which is verified by standard projections. Although alternatively, I can produce the answer with x minus 1 and projections, because they do integrate and work very well together. And we're going over here. This would be 1 and 6, so 6 projection there, and then the last one in that row is 1. Then I got 2 vertical ones come down, and then we got 1, 2, 3, 4. We got 5, 6, and 9. We have 5 across. So, and there's only 1 left in that row. So there, and then we go 6 And I pretty think I have it done. 9, 9, 5. That's the last one in the row, column, or box. And I can, like I said, I could apply x minus 1 and figured out that 5, even though it's the only one left. The formula is dynamic and can be applied at any stage to any amount of unknowns. It'll unify and verify answers, and it can actually work outside of standard and ghost projections. Well, sometimes you do integrate them for the to decide which everyone's each their own on their technique. Now the last ones we have here, that'd be 5, and the last one would be 4. We sign it. Kind of hard to sign on here. That is an explanation, and a little unorthodox. I normally do not. I'm gonna have to try to find some books that are harder caliber. I don't know. I'm gonna have to go online, try to find them, because I still prefer to do it on the old pen and paper medium. That is it. I am going to sign off. Duke out.